Hey everybody, welcome to the Caffeine Isolation Lab. Here's the outline for the video. I'll be going over the experiment in general and talking about the procedure. And throughout that, I'll also go over the sublimation technique. Then I'll show the experiment in the lab, and at the end, I'll look at the NMR, just because there are some things on there that we haven't seen before and I wanted to go over. In this experiment, we will be extracting and isolating caffeine from tea leaves. So we'll be using a tea bag and place that in about 20 milliliters of warm water, like shown here. And we want the water warm, but not necessarily boiling, because there are other compounds in the tea bag, like tannins and gallic acid or particulate matter, all of which will complicate the isolation process, and those will come out easier if the water is boiling. To help ensure that these compounds don't contaminate the caffeine product in the end, we'll dissolve some sodium carbonate in the water, and this just helps keep the tannins and gallic acid in the aqueous layer when doing the extractions. Gallic acid and tannins have acidic groups on them, so by using sodium carbonate, we can deprotonate those groups and ionize the molecules so that they remain in the aqueous layer and don't follow caffeine into the organic one. After allowing the tea bag to sit in the water for about 20 minutes, we'll extract the aqueous tea solution with methylene chloride. There will be a good amount of tea solution, so we'll end up doing 6 to 8 extractions to make sure that we get enough caffeine out, and we'll spread that solution out between 2 polypropylene test tubes. The other compounds in the tea solution make separating the two layers fairly difficult, and we're going to end up seeing emulsions between the organic and aqueous phase. So to help break this, we're going to centrifuge the test tubes during each extraction. Once we have the extracts, we'll dry them over sodium sulfate until it's free-flowing, and it's very probable that a good amount will be needed just because it is difficult to separate the organic phase cleanly from the aqueous one during the extractions. Then, once removing the methylene chloride solution, we'll want to rinse the sodium sulfate a couple more times with some more methylene chloride to help reclaim any caffeine product that would have been left over in that much drying agent. The methylene chloride solvent can then be evaporated, and the crude product will be purified through sublimation. For this, we'll be using a Bunsen burner and a cold finger. And here's how that technique is going to work. After drying the methylene chloride solvent, the crude caffeine product will be gathered on the bottom of this filter flask, and in that flask we'll have inserted a cold finger, which is just a test tube that is filled with ice to help create a cold surface. We'll place the flask over a Bunsen burner, and as it heats up, the caffeine will undergo sublimation, going directly from a solid into a gas. As the vaporized product rises, it'll interact with the cold surface of the cold finger, and it will condense onto that surface. Now, there are some criteria for this technique. The solid product must be able to vaporize without melting, so it has to be able to go directly from a solid to a gas, and the product has to vaporize without decomposing at those higher temperatures. Then the product must also be able to condense back onto a surface, and the impurities cannot also sublime with the product, or else you're just transferring an impure product to a different surface and didn't really do anything to purify it. Then we can characterize the caffeine by measuring its melting point and running an IR spec. Now, when taking the melting point, we'll want to set the apparatus about 10 degrees lower than the literature value. Because caffeine can sublime, it's pretty likely that it'll start melting at a temperature a bit lower than 236 degrees Celsius. And in the end, we'll calculate a percent recovery by dividing the weight of the caffeine isolated by the weight of the tea bag where we isolated the caffeine from. I'll first weigh out the tea bag so we can later calculate the percent recovery. And I'll put about 20 milliliters of water into a beaker. Then I'll weigh out 1.1 grams of the sodium carbonate, which will be used to react with the gallic acid and tannins. And I'll place that in the water, mixing it around until it's fully dissolved. Now I can put the tea bag into the water, placing a watch glass on top, just so that we don't evaporate too much water off as we heat it up. We'll let the tea bag stay in there for about 20 minutes, monitoring the water just to make sure that it doesn't start boiling. After that time has passed, I'll remove the tea bag and drain some of the solution out, being careful not to rip the tea bag. Then the aqueous tea solution can be transferred to these two polypropylene test tubes where I'll be doing the extractions. And I'll be using methylene chloride as the organic solvent for those extractions. Initially, when I add the methylene chloride, there's a pretty clear separation between the two phases, but as I mix them together, you can start to see the formation of emulsions, which is going to make separating the organic phase difficult. So I'll put a cap on the two test tubes and place them both in the centrifuge for a couple of minutes to help separate the layers better. Now the organic phase can be distinguished a lot better, so I'll start transferring that over to an Erlenmeyer flask. And as I'm doing it, you can see that it's difficult to separate it completely from the emulsions and the aqueous phase, so I'll definitely need quite a bit of sodium sulfate later to completely dry that. But for now, I'll continue with the extraction process, adding some more methylene chloride and mixing the two layers together really well, then placing the cap on the tubes and putting them in the centrifuge for a couple of minutes so we can separate out the phases once again. And I'll end up doing this 6 times, so I'll skip to the 6th extraction where I'm removing the final extract of methylene chloride solution. Those extracts can then be dried over sodium sulfate, and I'll add that until it's free flowing. And I'm going to have to add a lot, mixing it really well with the methylene chloride to make sure that all of the aqueous tea solution is absorbed. Once that's done, I'll remove the methylene chloride solution and move it over to the filter flask where we'll be doing the sublimation. And I'll rinse the sodium sulfate with some additional methylene chloride a couple of times, mixing it really well to help reclaim as much caffeine product as possible. I'll combine all of the methylene chloride solution into the filter flask and begin evaporating the solvent using a stream of air and gentle warming. The product will gather on the bottom of the filter flask, and now we can start prepping the cold finger by filling the test tube basically all the way with ice. Then I'll place the cold finger into the flask so that it creates a seal at the top, and now I can start heating it up over the Bunsen burner. As it heats up, the caffeine will begin to sublime and you can see a gas forming inside the flask, and the cold finger will start to turn white as the product begins to condense on its surface. I'll hold it over the flame until there is no more solid product left on the flask, which means all of it should have sublimed and is now condensing on the surface of the cold finger as it cools off. Which you can see really well here. All of the solid caffeine product has now been transferred over to the cold finger. So I'll weigh the product now, first weighing out an empty watch glass, and then using a spatula, I'll just start scraping the caffeine onto that watch glass until I've removed it completely from the cold finger. Then I can weigh the watch glass with the product so that the percent recovery can be calculated. Now I can run a melting point, and I started really low just in case there were impurities and since caffeine can sublime. And it looks like and smelt like caffeine started burning before it started melting, but it started melting around 222.2 degrees Celsius and looked like it finished around 229.6 degrees Celsius. Finally, I'll run an IR spec using the neutral mole technique. And it looks pretty good. We can see the aromatic hydrogen around 3100 and the 2 carbonyl peaks for the compound around 1698 and 1658. So that turned out. All right, I wanted to go over a few things on the NMR for caffeine real quick. First off, notice how I've labeled both the hydrogens and the carbons on this molecule to make things a little easier in following this video and to keep things consistent for your TAs when they're grading this. I'm going to ask that everyone also label their hydrogens and carbons the same way. You'll also see that you are given some 2D NMRs, and these are going to be crucial for labeling all of the peaks. So I'm going to be focusing on these throughout the process. If we look at the 2D NMR included in the H&MR section, we can see that on one axis there is the H&MR, and on the other axis is the carbon NMR. And this one actually combines two different kinds of 2D NMRs. The first one we've seen before, het core, which shows coupling between hydrogens and the carbons they're directly bonded to, and those are shown as the red dots on this 2D NMR. The second one is similar. It's called HMBC, and it shows coupling between hydrogens to carbons that are 3 bonds apart, and is represented as these black spots on the 2D NMR. So here's an example of how that would work. If we look at hydrogen A and consider the carbons that it is coupled to, we can go 1, 2, 3 bonds away and see that it would be coupled to carbon 2. But it also sees carbons 3 and 8, both 3 bonds away, so we would expect to see 3 HMBC spots above the signal produced by hydrogen A. The other 2D NMR in the carbon NMR portion is a cozy, and just as a reminder, that shows coupling between hydrogens to other hydrogens that are 3 to 4 bonds apart. So in this molecule, that's only going to work for hydrogens A and B because they see each other 4 bonds away. But hydrogens C and D are too far away from any other hydrogens, so the only spots we will see above their signals on the cozy will be for themselves. To use these, we need some point of reference, so let's take a look at the H&MR and see if we can label a peak first. Each of the signals is a singlet, so splitting isn't going to help us, but we can consider chemical shift and integration. If we look at hydrogens B, C, and D, each of them are on terminal carbons attached to a nitrogen with an integration of 3, so we can expect all of their signals to be pretty similar, so it's got to be these 3 peaks here. Distinguishing them from each other is going to be difficult, so instead let's look at hydrogen A. It's actually attached to an aromatic ring. Since this nitrogen has a lone pair that is in conjugation with the 2 double bonds, that makes that ring aromatic, so we can expect the signal for hydrogen A to be in the aromatic range, like shown here. Plus, this peak's integration seems to be about 1/3 the size of the other peak's integrations, just confirming that this is the signal produced by hydrogen A, so we can go ahead and label that now. And since we have a point of reference now, we can label the rest of the peaks just by using the 2D NMRs. We already know which peak is hydrogen A, so I'll label that here as well. And the thing that's going to be easiest to use first is going to be the het core. So we can go up to the red dot above the signal produced by hydrogen A, and to the left, that signal is coming from the carbon that is directly bonded to hydrogen A, so that would be carbon 1. And the other 3 HMBC spots above hydrogen A are for the carbons that it sees 3 bonds away, so that would be carbons 2, 3, and 8. From here, you might be able to look at carbon 2 and argue that since it's sp3 hybridized, whereas carbons 3 and 8 are both sp2 hybridized, that carbon 2 should be the most shielded out of the 3, and therefore the top spot out of those 3. But if you didn't recognize that, or didn't want to leave anything up for debate, we can just look at the cozy now to figure out the next peak. The first spot above hydrogen A would just be itself, since it's the same signal, but the other spot above it would be for the hydrogen that it sees 3 to 4 bonds away, so that would be hydrogen B. Now that we know that, we can look back at the het core to see which signal is being produced by the carbon directly bonded to hydrogen B, which would be carbon 2, and this confirms our initial idea that carbon 2 would be more shielded than carbons 3 and 8. From here, we know that the 2 remaining HMBC spots above the signal produced by hydrogen A have to be for carbons 3 or 8, but just by looking at the carbons, it would be hard to argue which one is which, so instead, let's look at the HMBC for hydrogen B. If we look 3 bonds away, hydrogen B would be coupled to carbons 1 and 3, and we already know that the first HMBC spot above hydrogen B is going to carbon 1, meaning that the second one has to be going to carbon 3. And this leaves us with the final HMBC spot above hydrogen A being for carbon 8. So it's kind of like a little Sudoku puzzle, but the 2D NMRs are super useful and can help take away the guesswork or arguments when analyzing the peaks. That's as far as I'm going to go on the NMRs, but you can finish analyzing the peaks using the same strategies that I've just shown, and don't forget to label your solvents as well.